Hello everyone. This is my second video on a section titled Homogeneous Linear Equations with Constant Coefficients. In my previous video I worked on some second order differential equation examples, so hopefully you've seen that one. If not, please do. And in that I talked about different scenarios when solving that can come about when solving the auxiliary equation. Whether or not the solutions are real and distinct, or repeated solutions, repeated real solutions, or when the solutions are are complex conjugates. So again, hopefully you've seen all that, because I'm not going to go into all those scenarios again. We'll just take a look at some higher order differential equation examples in this video. I have 4 examples. Alright, so in each of the 4 examples, I am just have the same instructions. Find the general solution of the given higher order differential equation. Now this first example is a third order. Third order linear, right? Because all the coefficients on the derivatives of the dependent variable are, dependent on at most the independent. Let's say the independent variable is x here. They're all constant coefficients, right? Linear with constant coefficients, as was in the title of the video. And it's homogeneous. Homogeneous because of the constant term on the other side here being 0. Alright, so if you recall from before, when I did second order examples, when you have a linear homogeneous differential equation with constant coefficients, how we're going to start by trying to find the general solution is by letting y be replaced with e to the mx power. Pardon me, where m is a constant. And then I try to find values of m, that would make it so that this is a solution of our differential equation. And then, the first derivative would be m times e to the mx. The second derivative would be m squared times e to the mx. And this one's going up to, the third derivative, y triple prime, would be m cubed times e to the mx. And I substitute these into the equation, and I can divide by e to the mx. E to the mx is never going to be 0, for real values of x and real values of m. And we get what's called then the auxiliary or characteristic in some books I've seen. The auxiliary equation or characteristic equation, associated with this particular differential equation. And that in this case would be m cubed minus 4m squared minus 5m equals 0, right? It's a cubic polynomial equation. And I solve for m. This is easily factorable, right? You can pull m out. And then you'd be left with m squared minus 4m minus 5, which would factor to m minus 5 times m plus 1. And you can double check all this. So my roots, right, the roots of this equation, I'll call them, there are 3 different roots. I'll call them m1, m2, and m3. m1 would be, 0, has a multiplicity of 1. m2 is a positive 5, right, also with a multiplicity of 1. And m3 is a negative 1, also with a multiplicity of 1. So I have 3 roots, distinct roots, and in that case we can jump straight to 3 linearly independent solutions, fundamental solutions to this equation. So I can very quickly create the fundamental set of solutions to this differential equation, and that consists of e to the 0. I'm just replacing m with the m here in this e to the y equals e to the mx with these m's. Now e to the 0x is just 1. And then replace m with 5. Y equals e to the 5x is another solution to this equation. And replace m with -1. Y equals e to the -x is another solution, right? And these three, if you want to do the Wronskian or check in some other way, you can show that these three functions, y equals 1, y equals e to the 5x, y equals e to the -x, they are linearly independent and actually over the entire real number line. But again, I leave that to you to verify this. And being a third order, I should be finding 3 linearly independent solutions in the fundamental set. And once we have the fundamental set established, then we can very quickly state the general solution. Remember, the general solution is just any linear combination of the solutions from the fundamental set. So the general solution to this differential equation is y equals some constant, say c1 times 1, so just c1, plus some other constant, c2 times the second solution here, e to the 5x, and finally plus some other constant, c3 times the third solution in the fundamental set there, e to the -x. And here we go, right? And c1, c2, and c3 can be replaced with any real number you wish. All right, so y equals, obviously, again, for any homogeneous equation, y equals 0 is a solution. And again, replace c1, c2, and c3 with any numbers you want, and you'll get other solutions. You could also pretty easily verify that this 3-parameter family of solutions is indeed satisfying this equation. Just take the first derivative, second derivative, third derivative, substitute them, and you'll see that you'll get 0 equals 0. All right. Okay. So that was my first example where, again, all the roots of the auxiliary equation were real numbers and distinct. They were all different. They all had a multiplicity of 1. All right, so let's take a look at my next example. This one's written a little differently. And it's still the same setup. Instead of y and x, y being the dependent variable, x being the independent variable, in this particular example, u is the dependent variable and t is treated as the independent variable. Alright, so keeping that in mind, I could think of this as u triple prime, right, the third derivative of u with respect to t, plus, and then this is u double prime, the second derivative of u with respect to t, minus 2u equals 0. And so again, this is a third order linear with constant coefficients, and homogeneous, you got 0 on the other side here. 0 for the constant term. So if that's the case, I'm going to let u be replaced by e to the mx, just like before. Again, for these linear homogeneous differential equations with constant coefficients, we make this substitution when we start trying to solve it. Pardon me. Alright, so if we went to the third derivative and put this in and divide it by e to the mx, we get our auxiliary equation. I'll just put aux equation, right, like that. In this case, it'd be m cubed plus m squared minus 2 equals 0. Alright, now this one here is a little more difficult to factor. Right? It's not as simple. There's no greatest common factor other than 1. Pardon me. But I do see a root. And if you have a root, remember you could use the rational zeros theorem if you think back to maybe some pre-calc course you've taken to set up a list of possible rational zeros and then find zeros that way. But I can very easily see that m equals 1 is a root. Alright, this one's pretty easy to check. 1 cubed plus 1 squared would be 1 plus 1 is 2, and then minus 2 would be 0. And remember from, again, maybe some pre-calculus or college algebra you've taken before, that means that m minus 1 is a factor of this polynomial. Alright, and if you'd like to get the other factors, you can do some division. Now you can do long division or synthetic division. I'm going to do synthetic division off to the side here. You know, where I put the root down here, and then the coefficients of the polynomial, you know, 1m cubed, 1m squared, 0m to the first, and -2, and then separate my quotient from remainder. Drop the first. Hopefully you recall how to do long division or synthetic division like I'm doing. 1 times 1 is 1, 1 plus 1 is 2, 1 times 2 is 2, 2 plus 0 is 2, and 1 times 2 is 2, 2 plus -2 is 0, 2 plus -2 is 0, and you're getting the other factor from these coefficients here. So this m cubed plus m squared minus 2 factors to m minus 1 times m squared plus 2m plus 2. Alright. Now, like I said, we know that 1 is a root. Now we're just trying to figure out where is this equal to 0. Alright, where is m squared plus 2m plus 2 equal to 0? And you could use the quadratic, you know, it's not nice and factorable, but you could use a quadratic formula or completing the square. I personally like doing completing the square. So subtracting the constant, completing the square, and this factors now to m plus 1 squared equals -1. And m plus 1 is either positive or negative I. Remember, I is the square root of -1. So one root is 1 root to this equation, and then another root, m2, is -1 plus I, and then a third root, say m3, is -1 minus I. So I have the case where there's a real root with a multiplicity of 1, but then there's also these complex conjugate roots with multiplicities of 1. And again, if you hopefully you've seen my other video where I talk about, you know, what happens, what kinds of solutions to the differential equation are we getting when the roots are different kinds of roots, you know, real roots, complex roots. So I'm going to jump to the fundamental set now. The list of basic independent solutions to my differential equation. Again, when m is 1, just, you know, u equals e to the x, e to the 1x. And then this -1 plus 1i, -1 minus 1i, the solutions coming out of these two would be e to the -x, e to the -1x, times the cosine of positive 1x, and e to the -x times the sine of positive 1x as well. Again, please go back and look at my other video on doing this with second order. All right, and then putting any, you know, then any linear combination of these three is going to be a solution to this. Oops, shouldn't be x, it should be t. I apologize. I forgot, you know, the independent variable in this equation was t, so this would be e to the t, e to the -1t times the cosine of 1t, e to the -1t times the sine of 1t, right? And then from this I state my general solution. The general solution to this equation is u of t, right? You remember the independent variable was t, equals, you know, some constant c1 times e to the t plus, and then these last two terms are going to have e to the -t in common, so very often you'll see that factored out, times, and then some, you know, the quantity, some other constant c2 times the cosine of t plus, and then some other constant c3 times the sine of t. And close that constant there. Close that quantity. Where c1, c2, and c3 are, you know, any constant. All right, and just as I've mentioned before, right, you can pretty easily verify that this is the general solution, that this 3-parameter family works for this differential equation. Just take the first derivative, second derivative, third derivative. It would take a while, but and then substitute, and you would see that the initial equation would be true. And of course, you can replace C1, C2, and C3 with any constants, any numbers, and get a specific solution to this particular equation. Okay. My third example. All right, so far we've seen an example with distinct real roots, a real root, and some complex conjugate roots to the auxiliary equation. Let's take a look at a third example. So again, same instructions. Find the general solution of this. Now it's another third order linear homogeneous equation with constant coefficients. So here I'm going to say y is the dependent variable. Let's say x is the independent variable. I mean, you can make a t or some other letter if you want, but I'm going to let, again, for these homogeneous linear differential equations with constant coefficients, I'm going to let y equal e to the mx. And then we get our auxiliary equation or characteristic equation. And that in this case would be m cubed plus 3 times m squared plus 3 times m plus 1 equals 0. All right. Now again, this is, if you can't see how to factor this right away, you can try using the rational zeros theorem. Now the rational zeros theorem, the only possible rational zeros this polynomial has would be 1 and -1. Now 1 obviously doesn't work. You'd get 8 equals 0 if you plugged in 1 for m, but -1 does work. All right. M equals -1 is a root, and let's check that out, right? Because this would be -1 plus 3 is 2, minus 3 is -1, and then plus 1 is 0. And if m equals -1 is a root, that means m plus 1 is a factor. And then you can go through and do division, and I'll tell you right now though, 1, 3, 3, 1, remember those are the coefficients from the third row of Pascal's triangle. So I mean this actually factors to m plus 1 cubed, and I'll let you figure that out. I'll let you verify that. So this left side is m plus 1 cubed equals 0. So this is a root, but with a multiplicity of 3. Because there are 3 factors that -1 makes 0, with a multiplicity of 3. All right, and again, I talked about multiplicity. If a particular root of the auxiliary equation has a multiplicity higher than 1, how to create independent solutions in your fundamental set. So I talked about that last time, and I'm just going to do it here. All right, so the fundamental set, the fundamental set of solutions to this differential equation consists of the following: e to the -x, and then to get independent solutions to this, you just keep multiplying by the independent variable. So next one's x times e to the -x. And you keep doing this until you get a number of solutions, independent solutions, that's equivalent to the multiplicity. So I got 2 independent solutions, and then multiply by x again. You got x squared times e to the -x. There's a third independent solution. And there should be 3, right? We should have 3 total, being a third order equation. All right, and then now that I have the fundamental set established, our general solution, the general solution to this differential equation is the following: y equals some constant c1 times e to the -x plus some constant c2 times x e to the -x plus some constant c3 times x squared e to the negative x. And if you'd like, I mean, you could pull the e to the negative x out of everything. Be e to the negative x multiplied by basically a quadratic, c1 plus c2 times x plus c3 times x squared, where c1, c2, and c3 are any constant. All right. And again, please try, I'll leave it to you to verify. Take the first derivative, second derivative, third derivative of this, substitute into the equation, and you will indeed see that this satisfies the equation for any constants c1, c2, and c3. Okay, so we've seen 3 real roots that are different, one with complex conjugate roots with multiplicity 1, one where a root has a multiplicity higher than 1, and what we're going to see in my last example, we're going to see some complex conjugate roots that have a multiplicity higher than 1, right? Kind of combining the two, combining some scenarios. Right? So my last example looks like this. So find the general solution again of this. Now this is a fourth order, right? You see the fourth derivative of y with respect to x. And I could also think of this as 16y, the fourth derivative of y plus 24 times the second derivative of y with respect to x plus 9y equals 0. It's a fourth order linear with constant coefficients homogeneous equation because of the 0 on the other side. And if that's the case, again, we start off with this substitution. Let y equal e to the mx power and find these values of m. And we get our auxiliary equation. Which in this case would be 16 m to the fourth plus 24 m squared plus 9 equals 0. And I'm telling you, and hopefully you can see it, right? Hopefully you can see it. This is one of them perfect square trinomials. This polynomial here factors to 4m squared plus 3 squared. 4m squared plus 3, that quantity squared. And I'll leave it to you. You can check that pretty easily. Equals 0. And so when we're finding the roots, the only thing that's going to make the 0 is, when is 4m squared plus 3 equal to 0? Well, subtract 3, divide by 4, we'd have m squared equals negative 3 fourths. So m here equals, plus or minus I times the square root of 3 divided by 2. Right? Square root of both sides, and the square root of a negative, so it's got an imaginary part. But each of these, right? Each of these has a multiplicity of 2 because this factor is being squared. So each has a multiplicity of 2. Alright, so my roots. M1 is, 0 plus square root of 3 divided by 2 times I, and then with multiplicity of 2. And M2, the other root, is 0 minus square root of 3 divided by 2 times I. Again, with a multiplicity of 2. Each of these roots has a multiplicity of 2, and you see that they are complex conjugate roots. So the fundamental, the independent solutions that come from these, I'm going to start creating my fundamental set here. And I should, since it's a fourth order, there should be 4, linearly independent solutions in this fundamental set of solutions to the differential equation. So here you got, a is 0, b, if you think of these as a plus bi, a minus bi, a is 0, and b is the square root of 3 over 2. Now, you have e to the 0x, which would just be 1, right? So no need for that. And then one of these solutions will be the cosine of the square root of 3 over 2 times x, right? The cosine of bx. And the other one coming from this would be the sine of the square root of 3 over 2 times x. Now again, the multiplicity of each of these is 2. So there should be 2, corresponding to each of these. You have, and kind of like I did earlier, you take one of these, cosine of square root of 3 over 2x, and then times it by x. So x times the cosine of the square root of 3 over 2x. That's another independent solution to this differential equation. And then the same thing for the sine of x, multiplicity 2, so sine of square root of 3 over 2 times x, and then x times that, x times the sine of the square root of 3 over 2 times x. Sorry about the edge of the page there. But there's my fundamental set, right, four linearly independent solutions to this differential equation. And you can go through and check, use the Wronskian to verify that these are independent. Also, if you want, you can check each one individually, see that it does actually satisfy the differential equation. But now that I have my fundamental set, right, the general solution is just a linear any linear combination of these. So y equals, some constant c1 times, the cosine of square root of 3 over 2x plus some constant c2 times the sine of the square root of 3 over 2x plus another constant c3 times this x times the cosine of square root of 3 over 2x. And then finally plus a fourth constant c4 times this last solution in the fundamental set, x times the sine of the square root of 3 over 2 times x. And there we go. All right. Again, it's fourth order. You should be finding 4 linearly independent solutions in the fundamental set, and then the general solution is any linear combination of those. Okay. And again, it would take a little while, but you could go through and verify that this family of solutions does indeed satisfy the differential equation. This family of functions, right? Take the first derivative, second derivative, third derivative, fourth derivative, and then substitute, and you would see that indeed the equation is satisfied. All right. So again, different scenarios there when things have multiplicities higher than 1, when you have complex conjugate roots, when you have real roots that are distinct, all those scenarios came up at one point or another during my video. And I hope that watching me go over these 4 examples, and hopefully that the previous video also where I did second order equations that were linear and homogeneous with constant coefficients, I'm hoping that watching all these examples helps you out when you work on similar problems on your own. And thank you very much for watching.